Welcome everyone to this new video. In this video, we're gonna introduce a new topic, which is infiltration rate, and we're gonna solve a problem to review the curve number. And the type of infiltration rate that we're working about is the soil infiltration rate. And in this video, we're gonna use the Horton equation, which I'm gonna proceed to explain in the following videos, in the following exercises. Let's start with the first problem, 5.6. A hydrologist designing a stormwater drainage system requires an infiltration experiment for a new pond area to evaluate the infiltration characteristics of the clay loam soil. A ring infiltrometer test was made on the soil. The results of the test are given in the data table below, right here. The inside diameter of the infiltrometer is 35 centimeters and the area is 962 square centimeters. They ask us to determine the filtration capacity for the time intervals, find the initial infiltration rate, and the ultimate infiltration rate or final, using the Horton's equation. Um, Let me start by explaining what's going on here. So it's talking about a infiltration experiment, and it's talking about a double ringed infiltration test, which is something that looks like this. This consists on putting these two rings on our study area, and you are gonna pour water into these rings. And this right here in the center, it's a float. This right here, I think is plastic, so it's gonna elevate with the water. So as the water is infiltrating, the water depth is gonna be decreasing, and you can read that right about here because this has some it's like a tape. So you take the measurements of this every uh, given intervals of time. In our case, what's happening here is they are giving us the intervals of time that they took measurements, but they are not giving us the water depth or the measurement here. They're actually giving us how much water they added, and this is confusing because I think the reason they're doing this is to make this a little harder, but we work through it. Instead of giving us the measurements of the depth of water as they decrease while the water is infiltrating into the soil, I think they are giving us how much water they added to keep the level of this float the same throughout the whole experiment, throughout the 150 or 2 hours and a half uh, duration of this experiment. And given this water added, we're gonna solve for these other columns in this problem. So let's start by converting these minutes into hours, because we're gonna use hours at the end here in this column. So let's do that. Divide it. So we divide these minutes by 60, and that should give us hours. Yep. So 150 minutes is 2.5 hours. And in this column, we want to solve for the change in time. So each interval. So for the first one, it's going to be 0. And this is going to be 2 minus the previous timestamp. And we do that all the way down. So that means, yeah, we have these time intervals differences. And here the book provides the calculation that you need to do. Like the change in column 1, this is column 1 divided by 60 will give us the hours. So here I'm not dividing. I need to actually, so we did it for the minutes and we need it in hours. So we should have done equals this is hours minus the initial. Do those instead. So we get the units in hours. Hopefully I didn't confuse you there. Now we need to find all this water added. We need is in cubic centimeters. So it's including the area. If we divide it by the area, we get only the depth of the water in here, the elevation of the water between the surface and the surface of the water. So let's divide that by the area. Well, this is going to be 0. And we can divide this by the area. And the area is given. They're giving us The diameter is 35 centimeters, which ends up being 962 square centimeters of area. So I divided by 962, it gives us the depth of that water inside that ring. Um, so now the units of this depth or accumulation of water is in centimeters depth. Now let's compute the difference between each timestamp. So this is gonna be 0 again, and this right here is gonna be equals to this minus the previous value. And then we drag that down, and now we have how much water, let's say, we lost per each time interval. We lost due to infiltration, right? How much water infiltrated. And now we need to find the infiltration rate, which is going to be column 5 divided by column 2, because column 2 is in hours. So we're going to get the centimeters per hour. This is also going to be 0 equals to column 5 minus, no, divided our change in time. And then we drag this down, and that's for part A. Determine the infiltration capacity for the time intervals in the experiment. We have the infiltration capacity or infiltration rate per each time interval. Now part B is asks us to do the initial infiltration in Horton's equation. So that's, excuse me, that's going to be 9.35. That's the initial. And the final is gonna be this one. That's the final infiltration rate. F sub, oh, F sub C. So that's the answer for part B. And this is the answer for part C. Now, another way to visualize this is we can grab, let's say this is per hour. So we can grab this data here and plot it. Let's put it here. So this is the time in hours. Now let's grab the accumulation, which is these values here. And let's copy just the values. And this is accumulation in centimeters. And let's grab this as well, which is the infiltration rates. And let's copy the values as well only. And this is the infiltration rate in centimeters per hour. Now, the reason I get him back here is because spreadsheets is a little tricky to work with charts. I like Excel better, but we're gonna insert a chart. Let's click somewhere here, insert a chart that is empty, and let's proceed to use the line chart. And then the data range, it asks us to include the data range, which I will omit the zeros. I will just use this data because I don't want the zeros to be plotted. And then in an x-axis, we want the time, which is column C, C27 to 34. And we want to plot, first let's do accumulation. So let's remove C and E. Series will be the y-axis, as I understand. So in this case, the flow accumulation would be, let me see if I can add x-axis. Oh, I don't think these values don't seem correct. Let me see. Oh, I need to copy values only. Okay, now it makes sense. So this is the time, the accumulation, and the rate. Okay, good. So this will be the accumulation time versus accumulation. I won't lose time adding axi, the axi. So this will be the time, and this is how much water is being accumulated. And we can also plot the time versus the infiltration. Insert chart. Let's make a line chart again. data range, same process. The x-axis will be the C column, and then we want to use the E column for the y-axis. E27. So this will be the infiltration rate curve. I'm using a line chart. I think if you use a smooth one, I don't know. But it gives you an idea of how infiltration starts high, and it makes sense because let's assuming the soil is not saturated, there's gonna be more water infiltrating at the beginning. At the end of the 2.5 hours, there's gonna be less water going into the ground. So this is for this problem. I hope it helped you see what an infiltration rate is and what this experiment consists on. Now let's move to the next problem, where we need to use the curve number again. This is going to be a review of what we did in the previous video. And the book mentions something about direct runoff for impervious areas. I don't think the book is pretty clear on this. I think it has to do something with the notes that you will find in table 5.7. I don't have it in this picture, but if you go into the book, you'll find some notes. I believe part subscript B mentions something about what the book is talking. I will recommend you to go after, if you still need help after this video, to get a more exact or accurate answer. Ask for help. But I've got you up to the point where we find the curve number. So for the storage, saturated storage, and we find the runoff. And then you can ask for how to work on the assumptions. Now, to do that, let's start by reading the problem. Imagine a planned residential area that will cover 50 acres, with each house sitting on a half-acre lot. This area is in a region classified as hydrologic type A by the Natural Resources Conservation Service, NRCS. Before the development starts, the area is an open space that has good condition grass. Excuse me. We want to know how much water will run off this area during a big storm. The biggest storm we expect, the design storm, is 8.64 inches of rain. To calculate this, we'll use the NRCS curve number method. This method helps us estimate how much rainfall will become runoff based on the type of land, the land use, and how much water the ground can absorb, the soil type. Hopefully this is just a review from the previous video. What's happening, we have a pre-development and post-development case. So in the pre-development, we have here, let's use this here before. We have open space and good condition grass. If we go to our 5.7 table, we have open space, the category of open space and good condition grass. We know that the soil type is type A, so we might want to use number 39 as our curve number. Now, I have the equations here to solve for the maximum storage or saturated storage of our area and the runoff here. So with our curve number, now we can solve for the maximum storage of water, which is going to be equals to 1,000 minus the curve number 39 minus 10. I'm using this equation right here. We got I7, okay. So we got our maximum storage 951, and I believe this should be inches. Now, with this value, let me double check. I don't recognize the number, if that's correct. That's not correct. And that's because I'm using minus here and it's over. Okay, this is the actual value. The other value was way too high. So this is how much water the ground, let's say, can, up to how much water it can contain, it can store. And based on that, we can find the difference between precipitation and how much it can store, how much water is actually run off before it gets infiltrated or into the ground. So to do this, we use this equation right here, which I already have it set up here in Excel, so I don't lose time typing it. and we can just modify it, I think. So we got the precipitation, which is given is 8.64 inches. That's our precipitation for our design storm. Minus zero point 0.2 times K17, which would be the storage, the saturated storage right here. Um, all of that squared, all of that divided by the precipitation again, plus zero point 0.8. This is not 0.85, it's 0.8. That's a mistake, an error. Times the storage, which is K17 in my case, is the storage right here. So this gives us a runoff of 1.436. Yep. So this will be the runoff that we get before the development. And before I move on, let me correct this. Okay, that looks better. Now we do the same approach for the after, the residential. And if we go to our table, we have the residential category. And for half acres lots, type A, we have a value of 54. So we want to use that 54. And again, we solve for that. It would be 1,000 divided by the curve number equals to 1,000 divided by the curve number minus 10. And let's just copy this equation and just change the location. Just change the location of our curve number. So instead of K17, we're gonna use uh it will be K23 for our storage. K23, K23. The rest of it should be the same. Oh, except for the curve number. We need to use, not the curve number, we're using this the precipitation. Okay, no, we're good. So we get a value of 3.13. This is inches, and the runoff is inches. So as expected, we used to get only 1.44, I would say, inches of runoff. And after residential, after the development, we get more runoff. Um, so yeah, as I mentioned before, there is a little more to this problem, but it's not very clear to me, so I don't want to mislead you. So I will just suggest you to ask help to another professional or who knows how to solve this problem better. Um, let's move on to the next problem and last of this video. We're gonna go back to the Horton equation, and in this case, we just need to plug the values. I have it here already, but we'll go through them. We have two equations: one to find the infiltration rate of the water into the ground, and one to find the volume of the infiltration, how much water went into the ground during a given time duration. So the problem says a double ring infiltrometer is used to estimate a Horton type equation that can be used to predict infiltration rates and volume for a proposed retention pond. This retention pond is what I explained in the previous video. When you get more runoff, developers need to account for that extra runoff, and they create uh, retention ponds. The initial and final rates are 10 and 2 inches per hour. The initial, in this case, is 10. This is 2 inches per hour. This is the final. The recession rate is 1.5. The recession rate is the K value, 1.5 per hour. It's asking what is the estimate rate of infiltration after after half an hour of infiltration. So the time is 0.5. Also, what is the volume of infiltration in cubic feet, liters, and inches for a 1 acre pond infiltration area after 2 hours of infiltration? For the second part, we're going to use this equation down here. Note, Horton's equation is a mathematical model used to describe the rate of infiltration into the soil over time. It assumes that the infiltration rate decreases exponentially as the soil becomes saturated. And that's why we use the decretion rate right here with our exponent, with our e-value. So now we just need to, let's try this again. We just need to plot this equation, which is the final rate equals final rate plus the difference between the initial minus and the final times the exponent of negative k 1.5 times t, and that gives us 5.78, which that's what I got. So this is inches per hour. So this is the answer for the first question. All we're doing here is plugging and knowing how to use this equation, and this is to find the volume of all that water that infiltrated. We says the infiltration after 2 hours of infiltration, so time is 2 hours, and this is going to be equals to the final. Okay, let's do it by parts. So let's find the first part is gonna be equal to the final rate times t, which is 2 hours. Okay, we got that. Let's do equals to the difference initial minus final divided by k. Okay, and now do the other one, which is going to be 1 minus the exponent negative k times t, which is 2 hours now, and another parenthesis. And technically, we should just equals this plus the multiplication between this and this other value. And okay, that's correct now. This is the value that I should have gotten initially. Let's make this 9.068, and this is in inches. Okay, now we need to also solve, we got it in inches, we need cubic feet and liters. So let's convert this inches to cubic feet, and all we need to do is we're going to just do the conversions, which is gonna be times 1/12 to convert from inch to feet, and then we need to multiply by the area, which is 1 acre, and then we need to cancel that, convert those acres into square feet. So it's 1 acre, but to cancel that acre we need to divide it, multiply it times 1 acre times, there are 43,560 square feet in 1 acre over 1 acre, so we cancel acres and we have feet times square feet, and that's gonna give us cubic feet, and that's 32,916. That's correct. And now we need the same volume in liters, so we need to go from cubic feet to cubic meters and then into liters. So we got this cubic feet, and there are, cancel in 1 cubic meter, there are 35.314 cubic feet, and then multiply to get rid of the cubic meters. We need to multiply that in 1 cubic meter there are 1,000 liters in 1 cubic meter. So yep, this is the answer for, and this is liters. So these three are the answers for the second part. Okay, I hope this video you find it helpful. Don't forget to review the last part of this problem. And yeah, this is how we use infiltration rates using the Horton equation. And this is the double ring test that they mentioned in this problem. Okay, good luck solving these problems. See you in the next video.